So far we have seen about the forward difference operator delta and the shift operator E. In this session, we will think about another operator, the differential coefficient operator. It is represented by the letter capital D. When the differential coefficient operator operates on a function, say y equal to f of x, it becomes d f of x equal to dy equal to d dx of y, or dy denotes the differential coefficient of the function y with respect to x. So we may write d is equivalent to d dx. If we want to write the nth derivative of y with respect to x, then it could be written as d raised to ny equal to d raised to n by dx raised to n y. Now we shall find the relation between the operators delta, E and D. The relation between delta, E and D. Let f equal to f of x is a function of x. We know that d f of x equal to d dx of f of x equal to f prime x, or d square f of x equal to d square dx square f of x equal to f double prime x. If we operate on f of x using the shift operator E, we get E f of x equal to f of x plus h, where h is the interval of differential. We may rewrite the above equation using Taylor series method, like E f of x equal to f of x plus h equal to f of x plus h by 1 factorial f prime x plus h square by 2 factorial into f double prime x plus h cube by 3 factorial into f triple prime x plus etc. This is equal to f of x plus h by 1 factorial into d f of x. F prime x could be written as d into f of x plus h square by 2 factorial into d square f of x, where f double prime x is rewritten as d square f of x plus etc. So this is equal to 1 plus h by 1 factorial into d plus h square d square by 2 factorial plus h cube d cube by 3 factorial plus etc. into f of x. Now this term is, say, e raised to x, where x is hd, or this is equal to e raised to hd into f of x, or we may write e into f of x is equal to e raised to hd into f of x, or in other words, we may say that e is equivalent to e raised to hd. We already know that e is equivalent to 1 plus delta. Now we know that e is equivalent to e raised to hd, where h is the interval of differencing and d is the differential coefficient operator. Let's consider this term e equal to e raised to hd. Taking logarithm on both sides, log e raised to hd equal to log e, or hd equal to log e. So this is one relation. From this we may write d equal to log e by h, or we may write d equal to log 1 plus delta by h. This is another way of writing this. Or say hd equal to log 1 plus delta. This is equal to delta minus delta square by 2 plus delta cube by 3 minus delta raised to 4 by 4 plus etc. You are rewriting log 1 plus delta in this way, or d equal to 1 by h into delta minus delta square by 2 plus delta cube by 3 minus delta raised to 4 by 4 plus etc. So this is another relation between d and delta. These identities give the interrelationships between the operators. We may summarize the results so far as E equal to 1 plus delta. E is the shift operator and delta is the forward difference operator. Then we have another relation E equal to e raised to hd, where d is the differential coefficient operator and h is the interval of differencing. Or we may write log E equal to hd. This is another relation. Or hd equal to log 1 plus delta, where log 1 plus delta is nothing but log E. 1 plus delta is E. Or otherwise, you may write d equal to 1 by h into delta minus delta square by 2 plus delta cube by 3 minus etc. This is yet another relation. So these are the interrelationship between the operators E, delta and D.